minutes to like 20 minutes for her, and she's like, you should go.
Nice.
Okay.
Right on.
So let me see if my costume still fits.
You have just a one costume that comes out once a year?
Yeah, I moved to Michigan and I left a lot of stuff behind, so I used to have a trash bag full.
Yeah.
Like 6 costumes. It's just fun.
Which one did you bring?
The widow.
Yeah.
I grew up in a really small town, so trick-or-treating here in Grant's house is like really busy. Congested. There's a lot going on.
They have like a parade in downtown in Grant's House too? Ashland, there's like thousands of people come out.
But they have a particular street Chelsea says that they always do like really big on that street, and everybody just goes to that street. Anybody get their testimonials back?
I didn't check. Oh, wow. There was one question I went home tripping out about, like, sweet out about. And I looked it up and I'm like, oh no, cool, I got it right.
Nice.
But other than that, I'm not sure.
Thank you. Good. How are you?
Tired. Hello. How does that? Are we going over how we did on the test?
Not yet. I didn't quite finish.
Okay. Did I do okay?
Oh, I don't know. I don't like look at them.
How did you do this, Marissa?
Well, you know, I grade them anonymously. So, yeah.
So, what do we cover in the second part of the series?
A lot of like solubility, equilibrium stuff, and kinetics.
Will we do it with titration and all in there? Or is that in this?
I can't remember. Yeah, I mean, we do titrations like throughout.
So what's our final subject in chemistry?
Like third quarter?
In this circuit, yeah, third quarter.
Third quarter, I mean, we start talking a little bit about like CHEM and like transition metals and this like kind of hodgepodge of things.
So transition metals are really like wonky then compared to everything else.
I mean, kind of, yeah.
I'm really excited to start getting up to the higher levels, especially the next biology class in the circuit, because that's when we start doing dissections.
Nice.
Can't wait to start testing my skills. I practice suturing for fun sometimes.
All right, let's get started. And so I'm sorry to disappoint. I didn't quite finish grading the midterm. So right, I kind of grade it one page at a time, and I grade the whole class, right? So I grade it pretty consistently. So I only have one or two questions left. I didn't quite finish. Overall, I think they're looking generally okay, and I think you kind of know if you did well or not, and if you maybe struggled, you know, just kind of take notes and, you know, look forward to doing better on the final, hopefully. So we, like I said, I didn't finish, so I don't have any stats or anything, so we won't worry about the midterm. That being said, right, chemistry is cumulative by nature, so I'm not going to go and like explicitly quiz you on a bunch of stuff from the first half, right, but it's all going to build. And then we do have a pretty fun lab this week, so make sure you pick up the copy. And then hopefully you're wearing pants, since we're going to be working with nitric acid. So Thursday, people, don't forget your pants. I should have sent out an announcement. And then kind of other things on the radar, things that we talked about. So obviously, again, the SNAP benefits have run out. So if you were benefiting from that, or even if you weren't, and you find yourself in need, right, reach out. You can always email me. So some of the faculty members on this campus, we're trying to get Aussie's covered established, and so we're trying to like determine if there is a need. So if you are in need, again, please email me and we can try to direct you to resources. So kind of what RCC is doing right now is they're just kind of posting a list of all the local food banks. But kind of what I've been hearing from the online chatter is that the food banks are running out of food. So I don't know what people's like personal experiences are, but that's kind of what I'm hearing. So if you need help, again, just email me and we can kind of figure out how best to coordinate resources. And RCC is going to do like a food drive too, so you can both donate and then I think also receive help at some point. And then other things, just don't forget about scholarships. I believe I posted the link to that Massachusetts scholarship, so apply for that. And I think I need to email a few people personally about things that you'll ask me about, but I'll hopefully do that today. Other questions, comments, concerns? And then don't forget the Blackboard, the reading questions. So I saw people kind of catching up on that kind of over this weekend. But don't forget about those. And then I think I sent an announcement about that. So the inner chapters, right, they're like kind of separate. They're like an extra book. I think they were a separate book at some point. But there should be a link to the resources tab, and then you can find them online. So if you have difficulty finding it in Blackboard, just send me an email and I can give you a direct link. And then just kind of other things. So I'm, again, a little behind on the abstracts now and grading your labs since I was focusing on your exams. But overall, the abstracts are kind of looking good. I may start grading them like just a little bit harder. I've been like pretty much giving everybody full points as long as you put in effort. But I think they're like coming out really nicely, you know, good succinct summary of your results. Just be sure to add in, again, kind of your little data points. And yeah, looking good. So again, I'll just keep kind of making my comments on those, and don't be surprised if I grade like a tiny bit harder, but honestly everybody's doing really well with those, so I'm pretty pleased with the writing. All right, let's dive in. So we're supposed to get through chapter 6 and 7 this week, so we'll see how that goes. And again, we're just kind of building upon our fundamentals that we worked upon in our first half. And so again, the whole point of this is we're trying to understand like why things are the way they are, why they exhibit certain properties, why do they bond the way that they do. And so, okay, we're just kind of setting ourselves up again. So again, we've established that compounds are composed of atoms held together by chemical bonds. And then basically, we can say that these bonds are the result of attractions. And so then we're asking, is it purely electrostatic interactions? And so the key difference, right, from an ionic versus a covalent is, well, you guys tell me. So what's the ionic bond? What does that involve? Yeah, Max.
The transferring of electrons.
Okay, so complete transfer of electrons. And we're going to, again, kind of look at this. And so usually, again, you get such a difference in their charges that you get, right, full separation, and then they're just held together by the electrostatic interactions. And like we mentioned, we have a cation, and that's the positively charged component that's going to be losing an electron, and then it'll be coupled with the anion that's negative and gains an electron. And so this is kind of compared to covalent bonding. And so what's kind of the general, what is a covalent bond? Go for it, Max.
Two atoms share electrons.
And so now sharing of electrons. And again, we'll kind of look at this because bonding is sort of a spectrum. And again, this is what like chemists are super interested in, is bonding, right? What makes a bond? Is it a single bond, a double bond, right? Is it a weird, not quite a full bond, but just some sort of interaction? So that's all what chemists, right, care about. That's a lot of what their research is fundamentally about. And then based off of these different happenings, right? So whether you have an ionic compound, that dictates other properties, which we'll get into in a second. Again, versus covalent, where you have this like cohesive molecule. And then we'll save metallic bonding for later, so we will address it. But this is more just kind of summarized as a sea of electrons. But like I said, we'll save metallic bonding for later when we're looking at molecular orbitals and atomic orbitals, probably second quarter. But let's focus in on kind of our two main types of bonding. And again, right, we're kind of trying to figure out why substances behave in certain ways, why do they exhibit certain properties. And ionic compounds, so what do we generally say about ionic compounds? Do you know some of their properties? Yeah. So disassociate in water. So good, we're going to look at why that is. What else can we say? We can also say soluble in water. I'll put soluble. Kind of. What else do we know about ionic compounds? Yeah.
Are they usually in crystal-like structure?
So usually very crystalline, yeah. That being said, right, you can get covalent compounds to crystallize, but yeah, they tend to be kind of more crystalline structure, kind of alluding to this crystal lattice structure, which we're going to be looking into. And so what other properties do ionic compounds have? So pretty crystalline, and then, yeah.
High melting point?
Good, so that was the other one I'm looking for. So right, high, generally melting points or boiling points. So right, trying to think of the boiling point of salt. I mean, that's got to be incredibly high. In your flame test, right, that I missed out on, so again, right, why you need it to be in the Bunsen burner is it has to be super, super hot, right? So you're right there at kind of its melting point or pretty close. Other properties, there's one main other one that we're missing. Kind of going with the crystalline. And you can kind of think, like, what happens when you try to, you know, cut them or smash them or... Yeah.
Brittle, like they break in shards?
Yeah, so that's good, right? So brittle, and I like how you said it, that they break in shards, because all that is pointing, again, at this structure here. So, and, right, I like this picture. We have our crystal lattice structure, our repeating units, and again, we'll kind of dive into why they are so. So notice, right, sodium is small, and we'll look at why it has that contracted radius versus our chloride ion. And so, yeah, just kind of imagining trying to take a knife and trying to slice it, right, it's going to kind of shatter apart, make these shards as you're really kind of forcing those electrostatic forces apart. And so then that compares to covalent compounds. And so covalent compounds, right, we could say they do not dissociate in water then. And I think I'll bring a demo on Thursday so we can kind of see what that means more. We won't get into solubility, but that being said, covalent compounds, right, tend to be insoluble or immiscible in water, or like slightly soluble. So maybe I'll just put like more soluble in organics. And I tend to start thinking about all sorts of drugs as well with like covalent compounds. And right, all of those are kind of small molecules. And so they're not going to be as crystalline again, right? You can get them to crystallize out, but they kind of tend to be more like powdery or different substances, right? And that's why we say the covalent compounds have these lower melting points, so they could also be liquids or even, right, gases. But that's, again, why we kind of tend to see them in these different states of matter. And we'll really get into, again, the intermolecular forces, I think, later in the course, which kind of dictates, again, what's what. And then any other things we want to say about covalent compounds? Yeah.
Harder to break apart? With more energy to break apart? Or is that not true?
Well, yeah, it depends. Like, so you're talking, they're kind of easier to break apart, like their intermolecular forces. Is that what are you talking about, like breaking their bonds? So yeah, their individual bonds are going to be strong. So individual bonds, yeah. So talking about single, double, triple, so all those have a lot of energy in them to break those individual bonds, right? And you can also think about the energy stored in those bonds and the chemical reactions. But then weak intermolecular forces. So that's the distinction there, right? So strong covalent bonds, but then kind of weaker intermolecular interactions, right? So then that leads to our different states of matter. All right, so that's kind of a preview of where we're headed. And so let's go back to our ionic bonds for a second. And so like we mentioned, an ionic bond occurs between our metals and our nonmetals. And so that's pretty broad, right? You have your entire periodic table, and most of them are considered metals over here. So, right, any of our metals bonding with our nonmetals tends to be an ionic compound. And again, this involves a transfer of electrons, and so usually you verify this as well with the crystal structure. And so like we mentioned, our metal tends to donate our electron, and I'll kind of add that, right? So it generally tends to supply your electron all the time, and then it loses it, becomes a cation. And so that's why I gave you that periodic table. So again, just kind of keep correlating everything, right? Everything should kind of reinforce itself. So then you can look at our group 1. Again, whatever kind of works for your reinforcement. So we have NS1, so that's why they like to lose their 1 valence electron, right? Our 1+ oxidation state. Group 2 is 2+, again, right, going back to their electrons. And then we'll kind of look at some oddities. And so again, right, our nonmetal then tends to gain our electron, so it becomes our anion. And so we see a lot of, obviously, oxide compounds, right, are pretty common in nature. Obviously, oxygen's very common. But then we might see a lot of our halogens or sulfides are pretty common. And then, of course, all these can exist. And so after they swap electrons, or one donates, I mean, now these oppositely charged ions attract one another and form our ionic bond. And so we have our ionic compound, which is our solid phase composed of our crystal lattice structure. So again, just this regular 3D array of these cations and anions. So that's something that we'll get into, again, a little bit later in the course. We'll take a deeper look at this. So that's something else, right, is like every substance crystallizes in a certain way and a certain pattern. So you can, again, characterize compounds by that and how they crystallize. And then, again, just take time to appreciate what happens in this reaction. Again, I wouldn't advise kind of doing this on a normal basis, but you can take sodium metal, So again, highly reactive, right? Pretty toxic. Obviously, you wouldn't want to ingest it since it'd be water reactive. And then same thing, right? Again, chlorine gas, pretty toxic. Yeah, actually, that's some fun fact that I was learning about. I'm a huge fan, obviously, of the Haber-Bosch process, right? The nitrogen plus hydrogen gives you ammonia, and so that was made by Haber. But apparently, he also did a lot of work in like chlorine gas and bombing people in World War II. That's chemists, but anyways, so right, take highly toxic chlorine gas used to kill people in war, and then you can mix them together, and that would probably be quite an explosive reaction to do. I'm sure somebody's done it on YouTube, and then we make nice sodium chloride salt, which again, safe to eat, right? And again, that's just emphasizing how dramatically too the properties change, right? Once they go from their metal form to their ionic form, so completely different properties. And same thing, right, when we start to incorporate these atoms into different substances, and their properties can kind of change.
Kind of tangential. How does salt develop naturally then?
Like, how do we mine it? I don't understand the question.
I guess, how did the salt end up in the mines? How was it developed, like, in the Earth's crust or wherever it came from?
I mean, Big Bang Theory, right? Because, like, I mean, everything was created, and then we could also go into the star development, right? How they make heavier and heavier elements until you get to, like, iron. But, I mean, that's kind of basically it. And, I mean, yeah, kind of Big Bang Theory or divine creation makes all the ratio of atoms, essentially, right? And then we just find them in their, like, salt form, right? So then that's the other question is we generally mine them as their halide form. And
I just mean, like, geologically, how did it, like, did it form from chlorine and sodium within the Earth?
No, I mean, it's just a bunch of processes everywhere produce sodium chloride. So yeah, I don't think we could, like, trace it. And a lot of it is just, like, you could mine it from the sea too, right? Like, so yeah, maybe I didn't quite understand your question. Because, like, the Dead Sea too, that's, like, another fun fact is, like, right, the Dead Sea is getting more and more salty as the evaporation occurs, so that's, like, one way.
Does it naturally occur, just like gold and platinum, or?
Yeah, but you're not going to find it in its elemental form, right? Like, I mean, you have all these elements that occur in nature, right? Like, there's a set percent abundance of all these different elements, right? It's just then how are they found, right? So then you go mine them by a certain process, right? So then you can take sodium chloride and then apply electrolysis, get out sodium that way, or like another sodium compound. But yeah, I don't know if that answered your question, but.
No.
All right, so then going back to our Lewis dot structures and also our electron configuration. So right, I kind of encourage you to use both, because these Lewis dot structures, you know, they're super simple, but they still give us a lot of powerful information. And so let's look at sodium chloride. And so just start off, right, give me the electron configuration. Let's just start with neutral sodium and neutral chloride. So just see if you can do that, and we'll go over it. All right, so what's the electron configuration of sodium? So neon, 3s1, excellent. And then chlorine, so what do we get for that one?
Neon, 3s2, 3p5.
Neon, 3s2, 3p5. Okay, so that looks good, right? No questions on that. If there are, again, right, flag me down. There's no dumb questions right now, right? We got to see how everything correlates. And so just to emphasize, right, so this is our valence electron. And, right, lots of different evidence for that. We could go back to the ionization energies. And then we can understand, and so this is kind of related to the ionization energy, which is why I kind of bring it up, right? So whatever that first ionization energy is, that's essentially what we're doing, or part of the process, right? So now we've lost an electron, and we can write our electron configuration for sodium. So what would it be? So it's kind of obvious from here. So neon. And then again, we can tell what electron we were losing. So again, we lost it from our 3s1. And then we can tell that, again, chlorine, right, really wanted that electron. So we had 3p5, so 1 away. Again, correlate that to your oxidation states. So these all have a -1 oxidation state, so showing that, again, they want to gain 1 electron. And so technically, this gets into electron affinity, which we'll cover at some point. Well, we'll save it before I get too excited. But essentially, you can measure the energy of, again, this process of taking that, and it would be favorable for chlorine. And so now what's our new electron configuration of our chloride?
Neon at 3s2, 3p6.
So 3s2, 3p6. And again, now we can see, okay, that's good. And we filled up our p orbitals, so now we have, right, our stable octet. So kind of going back to our octet rule. All right, that looks good. And again, right, we could label these kind of our core electrons, which...
Wouldn't that just be the electron configuration of argon?
Yeah, so then this ends up being, right, the electron configuration of argon. Better practice, I just like showing it still with the previous noble gas, just so we're kind of clear on that. All right, so that looks good. And then, so this chart down here is just kind of emphasizing our common oxidation states. And again, right, our alkali metals are always 1+, alkaline earth 2+. And then we'll get into a little bit of the transition metals. So again, we kind of like tease it throughout the whole course. So scandium and yttrium, though, are shown on here as 3+, right? So this is just telling us that they generally act as a 3+ oxidation state, even though, you know, kind of looking at its electron configuration. So argon, and then 4s2, 3d1, right? And so you can tell that these are all kind of acting as its valence electrons in that case, right? So that gives it a pretty solid 3+. And so the other thing to note is, right, this is all determined experimentally, right? People kind of look and observe what the most common oxidation states are, and then we can kind of get into the explanation as to why that is. So we're kind of slowly getting there. Again, just re-emphasizing that this is -1 oxidation state, and then our next group, right, our smelly family is -2. And so write that on your periodic table. And then write nitrides, phosphides. So -3 when we see those, or arsenides, a little rarer, but. And then, right, we could have carbides, so not unheard of, but rarer, 4- oxidation state, so it's not included there. So I always say, right, this is our kind of switch here of 4+, 4-, but then carbon gets into covalent compounds as well. And then aluminum's another good one to note, so that's 3+. And then other ones that we should note are zinc. So zinc is always 2+ for its oxidation state, so you can kind of see why that is. So again, electron configuration argon, 4s2, 3d10, so you can tell that it's pulling right from the s orbitals for that. And it does that pretty consistently, and right, it doesn't want to disrupt its full D shell, so it's just generally 2+ oxidation state. And then for our Gen Chem purposes, silver is generally considered to be in the 1+ oxidation state, but again, if you go research articles, you'll find that silver can be in like 2+ and other oxidation states, but again, for our purposes, always 1+. So this is considered one of those knowns. All right, good. All right, so now, again, we're getting into ionic compounds and more about those. And so like we mentioned, so they're from this complete transfer of electrons. We have our cations that are metals, and anions are nonmetals held together, again, not really by a bond, but just by electrostatic forces. And so I'll bring our cheat sheet. So this is kind of coming slowly, but these polyatomic ions. So right, so far we just focus on kind of binary compounds, so sodium bromide. But I'll bring the sheet for Thursday that has all the polyatomics, and we'll get into that. And so like we mentioned, I think earlier, our basic unit of our ionic compound is our formula unit, and that is the smallest electrically neutral collection of ions. And so again, right, they're just in repeating units, and it's going to be, again, giving your ratio, right, for these. So you're not given a discrete formula, just a ratio. And so again, right, sodium chloride is in a 1-to-1 ratio, but you're never going to find a discrete sodium chloride unit. And then, so ionic compounds always contain a positive and a negative ion, and so the sum of the charges of the cation should equal the anion, with your formula reflecting your smallest whole number ratio. Let's practice. Oh, well, actually, let's look into the conductivity. And so let's talk about what happens kind of in water and why they're conductive. So let's look at water for a second. And so first of all, what can people tell me about water? What do we know about water?
It's adhesive and it sticks to itself and other things.
Okay, that's good. What did you say?
Polarized?
So polar, okay, so that's kind of a good explanation as to why. So yeah, I like that. So polar, and then because it's polar, right, we notice properties such as kind of adhesive or sticking to itself. Good. So that's good that we notice that. Okay. So let's look into, well, why is water polar? And so what do we know about oxygen?
Negative.
So yeah, it's pretty electronegative, right? So we mentioned, well, fluorine is our most electronegative. Well, actually, I don't remember if we've officially covered that in class. Okay, so we might have to do some periodic trends. I think that's coming up in today's notes. If not, we'll cover them. So yeah, sorry. That's always a problem with chemistry, is there's always so much in the beginning. So yeah, a quick aside on electronegativity. So electronegativity, like I said, right, I wanted to get into our electroaffinity calculation, but let's just look at electronegativity. And so does anybody know what this is a measure of? Yeah.
How strongly it pulls electrons through it?
Yeah, so how strongly it pulls electrons, and then you're just missing like one.
That's all I got.
So in a bond, so how strongly it pulls electrons in a bond. And so good. So right, this is the caveat, right? So this is a measurement made, again, when it's with another atom, right? So it's bonding to something. So you're seeing, yes, how much it's pulling. And so that being said, fluorine is the most electronegative. We can kind of start to understand why, going back to our arguments about like radius. So again, as we go across the periodic table, we're filling in our same orbitals. And so that means that fluorine, right, really wants an electron. It's close to the nucleus, so it's going to be really pulling things towards it. So that's why it's the most electronegative. And then like you were saying, okay, well, oxygen's right next to it. So that makes oxygen also extremely electronegative and polarizing. And so let's go back to our diagram. I was drawing somewhere, sorry. And so we can also draw out, so I want to keep in mind our Lewis dot structure of oxygen. And so now we're kind of seeing how our polar covalent bond is formed. So hydrogen, they're each contributing one electron. So right, I just want to show our lone pairs. So we're keeping this in mind for its geometry. And so that's another thing to kind of keep in mind as you go through this whole series is, right, chemistry occurs in 3D. So you always kind of want to be trying to think in 3D from these little flat images, right, on the piece of paper. And so here's my water molecule. All right, so there's our water molecule. So again, it's got lone pairs. That's what is putting this in its shape. And again, extremely polar. So if we were to draw an electrostatic potential map, we would have much of our electron density right around our oxygen, and then very little electron density around the hydrogens. So trying to draw this in color. So kind of red, again, for high electron density with our lone pairs, and then green for kind of more positive. And so often this is written as creating a partial negative and kind of these partial positive regions. All right, so now we're understanding kind of why it is polar. But now what happens when we're in solution, right? What happens to our little, so now I have, right, our sodium chloride. So it's coming along, and right, our sodium's our small one, chloride's our big one. We'll get into exactly why in a second. But we said that it disassociates. And so now we can start to understand why that is. So I get my magnets. Oops. And so as you might imagine, and you can tell from my little molecules, so this is my chlorine, right? And so what end is attracted to our chloride? What end of the water? Can you tell from my structure here?
The hydrogen.
hydrogens, right? So chlorine is negative, so we just said that these hydrogens have a partial positive charge, and so that is true. So they start kind of surrounding and orienting themselves. Sorry, I'm like trying to draw a hydrogen. And so they kind of orient themselves towards the chlorine. And again, I apologize, I'm like kind of the worst artist here. And so I'll pass this water kit around so you can kind of play with that. But that's what happens, and it gets completely surrounded, right? So our chloride then, oops, as I drop water everywhere on the floor. So it gets completely surrounded and nucleated, right? So that is literally why it's dissolving, is because it's being surrounded by our water molecules. And then the same thing, yeah.
So are they surrounding it and then they're breaking the ionic bond by having like a stronger pull with the charge?
Yeah, so now you're getting into it. So this is, that's exactly what we're thinking of. So let's go back and kind of describe this better. So yeah, exactly what you described is kind of what drives solubility. So right now, right, we're just kind of getting into the basics. Later we'll kind of look at other trends, but yeah, essentially that's what's happening, right? We have, let's just imagine you throw in a fat crystal of salt into your water, and then literally what's happening at the surface is this, right? So then the other one, my sodium, is getting nucleated, right, and surrounded. And so exactly, so you have what's called your solute interactions, right, which is just basically those electrostatic forces keeping it together. And then you're saying, is the water, are those electrostatic forces strong enough, right, to break those solute interactions? So versus solute solvent. And so again, all we're saying is in this case, so obviously our solute solvent interactions are pretty strong in the case of our ionic compounds. And so again, now our sodium, and you can see it in my little models here. So right, which side is pointing towards our sodium now? So oxygen, right, with its partial negative charge, so that's attracted, again surrounding, nucleating it, coming along, right, and like you're envisioning kind of ripping it off slowly from our giant crystal, right? So then it slowly dissolves over time. Excellent. Yeah.
Can any like a polar covalent bond that's strong enough basically break apart ionic bonds then?
For the most part.
Special property of water?
Well, yeah, so it depends on like the polar solvent. So, right, you can have another polar solvent and that can potentially dissolve ionic compounds. That being said, right, there's a few exceptions to like the solubility rule, or like things that are insoluble, for example, right, like silver chloride is super insoluble, but I think part of that is like from how small, I think one of their radiuses, I think it's the silver, is like kind of tiny, which holds it like really, really close. So therefore, right, the solute-solvent interactions are not very effective, so then it is super insoluble. But yeah, that's kind of the general gist of it. And then you can have like, well, you know, now we're all over the place, but right, ethanol, technically a molecule, right? So covalent compound, but it's got a little bit of, again, we'll get to this like much later in the course, but this one has hydrogen bonding, which means that it's miscible with water, so there's a little bit of solubility there, even though, right, it doesn't have the full electrostatic separation. Does that make sense? Does that clarify for everybody else? Kind of makes sense what we're saying? So this is excellent. You guys are asking good questions. Oops. And I'm dropping my water. Here, start the water. So I'll let the water kind of float around the room, and you can at least play with, again, those electrostatic interactions. where are we? All right, so that again kind of summarizes why ionic compounds are soluble. And right, we say that this gets into why they're also called, right, electrolytes. Oops, if I could spell. So electrolytes, like I said, I think I'll bring a demo and then we'll see that. But yeah, it's pretty related to solubility as well, but not. Or all right, and then so looking at other kind of common oxidation states. So again, we just kind of want to see why things are certain oxidation states. And so kind of looking at what this is showing us. And so we're starting to get into some of these multivalent oxidation states. And so it kind of makes, let's decipher what your book is getting at. And so it says, so we're looking at metal ions with an 18 outer electron configuration. And so let's decipher what this is saying, right, and where the electrons are coming from. So let's just start with gallium. So write down the electron configuration for gallium. All right, so what do we get for our electron configuration of gallium? Argon, 4s2, 3d10, 4p1. All right. And so then we have gallium 3+. And so notice for a lot of these, right, your d electrons end up being like your core essentially. And so when you go to the 3+ oxidation state, it's pulling from our S and our P, right? So then our gallium 3+ just leaves us as argon 3d10 there. And so let's try another one. So let's look at tin. So write the electron configuration. So let's just start with neutral tin. All right, so what do we get for tin's electron configuration? Who wants to go for it? We haven't heard from this side of the room.
You can do it.
Okay, go for it. You're excited.
No, I was saying for them.
Oh,
I was like,
oh.
I can do it.
I thought you were like, I can do it. I'm so excited. What are we thinking? Eric, you have an answer? I was going to pick on Hector, but he walked out. Convenient.
I don't understand any of this.
Oh, okay. Well, let's go through this together, right? So we're just going through our electron configuration. And so, again, if you don't have your periodic table annotated with all the orbitals, so our 1s, 2s, 2p, right? All we're doing is we need to see our orbitals and what orbitals are involved, right? So we can kind of see how everything fits together. So 4s, 3d, 4p, and also, right, come see me in office hours if you're confused. It really comes together once this is labeled, right? 6s, and then we said lanthanide is 5d, 4f. Okay, I'll stop there for now. So 10, right, go back to the previous noble gas, because that's just always our convention, unless you want to start from the beginning, right? 1s2, but I'll start with krypton. So then start with krypton, and right, we just fill. I always say, right, we fill normally. The whole point of the periodic table is it tells us kind of our normal filling for electronic structure, right? So then after krypton, we go 37 rubidium, right, which starts 5s1, 5s2. Again, I'm just filling across. So 5s2. So we filled up our s orbital. Then we go to 4d, right? So 4d, 10. And then going over, so okay, 4d, 10. Now we're back to 5p. And so 5p1, 5p2. So 5p2. So does that kind of make more sense? Yes, no, no. So I still see no. So if it doesn't make sense, like, come see me, come talk to me. Like, this should be starting to like click together, and hopefully you're starting to see orbitals in your dreams. But now let's examine kind of why we have two different oxidation states as well. So notice, right, we have tin 4+, so this is a common oxidation state. And so if it's 4+, it's going to be pulling from our s orbital and our p, because again, right, we don't want to disrupt this stability of our happy and filled d electrons. So then tin 4+, krypton, and again, right, just leaving us with our kind of core electrons. And then what's interesting to note, and what your book is trying to point out here, is we have some ions, right, that are in different oxidation states. And so these end up pulling from the p orbital only, right, and then you're left with some in your s still. And so all that means, okay, let's look at this for tin 2+ down here. So tin 2+, and again, it's telling us that we're going to be left with some in the s orbital. And so now we can kind of tell why it's 2+, right? Because we have 5p2. So then, okay, it's going to pull 2 from the p if it's in the 2+ oxidation state, leaving us with krypton 5s2, 4d10 there. And again, right, all this is telling us is location of the electrons. And we need to know, like, our valence electrons, because that's where all the action is happening, and then we can talk about all sorts of things.
Well, I'm a little confused. Are you saying it would pull from the P if it can, and then it would pull from the S, and then it would pull from the B if it had to?
Yeah, I mean, potentially. Like, we don't generally see that behavior, but you're right. Chemists are always trying to push boundaries So yeah, it would lose the P first, probably, right? That gives us tin 2 plus. Then we said its other common oxidation state is 4 plus, so it likes to lose 2 from the S. And then, yeah, we'd have to look into like research to see if anybody has done any like weird oxidation states of tin. But yeah, that you kind of got the idea.
Is that ubiquitous though? Like, is it always going to be the p orbital, then the s orbital, and then like hypothetically?
Yeah, generally speaking. So that's what your book is getting at too with this, right? And we can go through like another example with like bismuth or thallium. But yeah, it's going to pull right from the P first and then start getting into the S's, and like generally does not disturb the D, right? So once we're back in P land territory, it basically just behaves like a regular P block, and then you're not disturbing that core. Is that kind of making sense? Question?
We would just know which of these oxidation states tin was in based on what other elements it was interacting with.
Yeah, so we'll get into,
We'll get that.
yeah, because we'll get into like naming if that's what you're asking. But yeah, like basically if you have like a random tin compound, you'd probably have to, I would say, like get a mass first, right, to see what is it paired with, and then that tells you oxidation state and all that. All right, but yeah, let's take a quick break. So let's take our 10-minute break, so maybe come back around 12:05-ish roughly. And then, yeah, we'll keep getting into it. So keep asking questions, and then get help, though, if you need it. we make it back from break. So before we look at these kind of naming, let's again kind of look at these electrons and how they fill, how that drives certain oxidation states, and then we'll kind of tease as to where this is going to. So try iron for a second. So just write down the electron configuration of iron. So what do we get for iron's electron configuration?
Is it 4s2, 3d6?
So yeah, I'll put argon and then 4s2, 3d6. Excellent. So that looks good. So do we all get that at least? And so now we can kind of figure out why it has kind of two common oxidation states. So iron is commonly either 2+ or 3+. So see if you can write the electron configuration for 2+. And again, you can probably see where that's pulling from, why that would be stable. And then see if you can figure out why 3+ is also stable. And so looking at iron 2+, so which electrons do we expect to go first?
S orbital.
Yeah, s orbital, right? So good indication. So 2 in the s, 2+, so good. That's going to pull from there, leaving us with 3d6. And then why might iron 3+ be another popular oxidation state? What can we say about our d orbitals? So argon 3d5, and again, right, that means that you have one electron now in each d orbital, so that tends to be stable. And well, I'll bring this up, but again, we'll kind of throw in a caveat. So iron 1+ is not common, and so what we might expect is, right, it might pull, I mean, either way, right, I think it might give us a 3d7 configuration, but then obviously, right, that would be unstable or potentially be unstable, as you have kind of two paired electrons, or again, we don't quite know where it's taking from, but iron 1, again, that's to say is it's kind of rare. And this is also to say, so this is kind of not really a good picture either. And so what we're getting at, so not complete picture. And so we'll come back to all these thoughts third quarter, because right now this is an oversimplified approach. What I mean by that is I've drawn these orbitals as degenerate, so right, all the same energy level, But once they start forming compounds and making different oxidation states, right, and different geometries, the different geometry changes, right, the location or the relative energies of these orbitals, right, so that has an influence. So that's why we're not really getting a complete picture with that, but that's where we'll take it to right now. All right, now let's get into naming, because again, we still have to figure out how to talk about these things and name them. And so previously we did the one type where we had, right, a metal that only forms one type of charge, like sodium chloride, sodium fluoride, right, calcium nitride, etc. And now we're going to focus on the second type, so the metals that can form more than one type of ion. And so we looked at some of those. So again, that's going to be our transition metals minus a few exceptions that we pulled out. And then those inner transition metals and P blocks, so those are the ones that we looked at, like thallium and tin and bismuth, right? So all those can have variable oxidation states. And in this case, so right, if we go back to our previous example, so let's take sodium nitride. Right, with these, we don't need to specify anything else because we can tell from the name how to write our formula. So we can go look at sodium, find that it's 1+, write nitride is nitrogen 3-. We said we have to write them in a balanced ratio, so we can come up with our formula, right, N3N. Well, what about, again, all these multiple valent metals, right? So it's not so obvious what their oxidation state is, or multiple charges as it's phrased. And so we have to note it in their name. Luckily, the convention has kind of changed for y'all. And so all you have to do is write their charge as a Roman numeral. So let's look at that. All right, so what we do, so here's kind of our table. And so looking at like chromium 2+, for instance, so if we have chromium 2+, then we just write chromium and then 2 in Roman numerals, and then the rest of our formula there. And then I've also included this chart with the older names, especially if you're like working in a chem stock room, right? You never know what names you might encounter, or if you go raid somebody's old lab, you might see older conventions of naming. For example, right, you see a lot of ferric chloride, so ferric. So the ic refers to the higher common oxidation state, so that would be iron 3. But again, right, kind of why they moved away from this system is, well, this is based off of 2 most common oxidation states, but again, many metals have multiple oxidation states, so the Roman numeral is a lot clearer. And so we'll practice on this so we can tell, right, we have, let's say, looking at copper 2+ versus copper 1, right? Again, we need to balance our formula. So we have copper 2+, right? Oxygen is in a -2 ratio. So copper 2 oxide is going to be CuO, right? Versus copper 1 oxide. So copper 1+, oxygen 2-. And so right in this case, we need Cu2O. And so again, whatever you need to do, so like star it and put your Roman numerals, right, give our oxidation state. So not how many, right? oxidation state. So let's do a little bit of practice with that. All right, so see if you can name these. So you might have to, right, use the formula to figure out our oxidation state. All right, so try those examples. Yeah.
If you have two oxygens, do you make it the dioxide in this case?
Well, in this case, you just want to put oxide, right? Because you're going to balance it from the name, right?
Okay.
So you can get the formula back out from the name. But yeah, we'll see that. Oh, yeah, sorry. So let's try to go through them and see how they went. So what do we get for this one? So what was the oxidation state of nickel? So +4, right? So you should have gotten that. So each oxygen, -2, right? And then you can, however you want to do this in your head, a little algebra. So -2 times 2 is -4. And then, so that's how you get, right, +4 to make a neutral compound. Good. So what's the name of this one then? So nickel 4 oxide, good. And again, right, just use a Roman numeral for this one. What about this next compound? How would we name this?
Tungsten 6 chloride.
Tungsten 6 chloride, good. Questions on that one? So again, right, same process. You can look up your chlorine. -1 oxidation state, -1 times 6 gives us -6. So then tungsten has to be +6 there. What about this one down here? What's the oxidation state? +2, excellent. So iron, oops. And again, I'll use a Roman numeral instead of ferrous or anything. So iron 2, phosphide. Good. And again, do some algebra, right? Phosphide, -3, so -3 times 2 gives us -6. You could also, this is a great time to look at the, what I call reverse swap trick. And you can see, right, we can kind of back this out, our exponents, and that's another kind of easy way to solve the algebra. What about this one down here? What's our oxidation state? So 2, so then we have palladium 2 sulfide, and then last one down here, excellent, so tin 4 oxide, and then so I'll point out the swap trick or reverse swap trick. Well, first of all, so have you all seen like the swap trick? So right, let's say we're trying to come up with the formula, right, for let's say manganese 4 phosphide, right? And so the swap trick is just like the easier way to set up the algebra, right? Because you have some sort of x plus some number plus the y plus your number, right, equals 0. So the easiest way to solve for these two variables, right, is to swap your y and your x values. So that's where the swap trick comes in. And so then, right, you kind of have the algebra set up this way, and you can swap their oxidation states, right, to be their subscripts here. And so you can see, right, that's again the easiest way to solve the algebra. And so then you can kind of reverse that. But I want to point out where it has some issues. So right, if we do this tin oxide over here, so if we're trying to do what I call reverse swap trick, right, and back it out, you can kind of see what happens, but then you can figure out that you're off by a factor, right? So you back it out, and then you end up with -1 for oxygen. But that's where you always kind of double check yourself, right? So we know oxygen should be -2, And so then I would just multiply this, right, times 2 to get to our appropriate numbers there. So just kind of watch that when you're doing these little algebra tricks, right? Kind of double check everything. Kind of go back to your standards. So again, right, oxygen is always -2 for our oxidation state, so that really helps you. And then our halogens, -1, so just base everything off of that. All right, good, we'll skip that for now. All right, so now let's look at kind of other trends and things. And so wherever my water is making away its round, we can see this. And so now we're looking at these trends. And so again, if you notice on either our picture or if we go back to our sodium chloride lattice structure, right, we notice kind of this difference in size of our cations and anions. And so let's see what happens. And so as you might expect, your cation radius is smaller than, right, your normal neutral atom radius. And so that makes sense. And so let's just kind of think about that. And so we can look at, let's just zoom in on lithium. So, right, so thinking about lithium, again, it's going to lose our NS1 electron, right? So now our outermost shell is gone. And so now we can imagine why that would cause a contraction. So you have that effect, right? But then you also have a larger effective nuclear charge. And so that's what it's saying here, right? So the loss of our electrons results in the remaining electrons in the atom experiencing a larger effective nuclear charge. So right now they're being kind of pulled closer in. And notice, right, with the greater charges, right, so as you get to the higher charges of like 3+, for instance, then you're going to have, again, more of that contracting effect, right, from that greater effective nuclear charge. And so, again, that's why we have it decreasing across, again, just comparing, right, our 1+ versus 2+ versus 3+ radius. Again, it's contracting from that greater effective nuclear charge. Obviously, as we go down, right, we still have more onion shells, so that's larger, but again, contracted compared to our metal atom. So that kind of makes sense. And then, right, we're given our radii here, so you can refer to that for other problems. And so then we get the opposite effect for the anions, right? So now we have kind of more electrons, and so our nucleus, right, that's positively charged has a harder time kind of hanging on to them. And so now they have a smaller effective nuclear charge, right, since it can't hang on to them as well. And so that means compared to our neutral atom, right, it has a larger radius since it can't hang on to those electrons as tightly. And then obviously they get larger, again, as we add more onion shells. And then again, as we go to the right across the period, we increase the effective nuclear charge. So we, again, having slightly smaller anions. But we mainly, again, want to compare that our anion is much larger than our neutral. And so again, I think that's reflected in those little models wherever they are, so you can appreciate that as well. And so again, just kind of a fun graph comparing that, right? So our neutrals are all in green, and then the common respective anion or cation in the colors. And obviously, right, transition metals, the radius, if you kind of remember, the trend tends to kind of flatten out since there's a lot of oddities, right, because of those d orbitals shifting around, so that can kind of flatten out our trends there. But then, again, what we expect, kind of our contracting radius there of our cations. All right, so then here's electron affinity. I knew we were going to talk about it soon. And so the reason, again, why I made a big deal is because I often compare electron affinity to electronegativity. So kind of, right, compare to electronegativity. And that's why I emphasize, again, that electronegativity is a measure of how much it pulls in a bond versus our electron affinity. And so now let's look at what our electron affinity is measuring. And so this is a gas phase calculation. And notice that this is just centered on an atom, right? So it's a different calculation. And so now what we're measuring is, right, how much energy, and tends to be exothermic, but again, we'll look at cases where it's not favorable and it's actually endothermic. But we're trying to figure out what does that energy look like? Again, how favorable of a process is that to add an electron to our metal? And this is kind of opposite, right, from ionization energy. So ionization energy, we were ejecting an electron, and now we're adding one, right? So now we're making a negative anion species and seeing what is the energetics of that. Does that make sense? So this is kind of like the other half of our sodium chloride reaction, right? So going back to the beginning, where we had our sodium and chlorine coming together, right? So that's half of that calculation. So we said we had one, energetically speaking, to receive that. And so again, that's what that is measuring with our electron affinity. And the more energy that is released, the larger the electron affinity. And again, we're kind of looking for a more negative number. And so let's look at these. And so there's just one kind of small discrepancy here from what we might expect. So again, let's just kind of look at these trends. And so these electron affinities are in kilojoules per mole. And let's take a second to look at it. And so what do you notice? And kind of, you should be thinking about electron negativity and kind of what the discrepancy is. So looking at these numbers, so which one is the most favorable? Which one has the most, the most negative, right? Because that's what we're saying with this. So chlorine, right? So we're looking at our numbers. And so, okay, so chlorine has the most negative number, so meaning, right, that's most exothermic, so that's generally considered favorable to have this exothermic reaction, right, releasing energy. So that's good. But then what do you notice? What's kind of odd about chlorine being our most negative one? What does that kind of not agree with? Yeah.
Fluorine has a smaller radius.
Sorry, which one has it?
Fluorine?
Yeah, so fluorine, right? So fluorine has a smaller radius, and then what else is it the most? So what did we say it was earlier? Did you say it?
The most electronegative.
Yeah, so right, so it's the most electronegative. And so we at least should look at this discrepancy and kind of, right, reason through it. So again, right, it kind of follows similar trends like we saw with electronegativity, right? So as we fill in our orbitals, it tends to be more favorable. But what causes this discrepancy? And so a lot of people attribute it to the difference in radii. So, I mean, you did mention, right, so fluorine has a pretty small radius. And so that being said, right, smaller things are worse at distributing a negative charge. So that means, right, since chlorine is slightly bigger than fluorine, it's better at stabilizing that negative charge. And then, of course, right, we still have the factors of it being, right, relatively close to the nucleus, again, kind of like comparing it with bromine in that sense. So again, thinking about your shells filling up and getting close to that noble gas configuration. But yeah, so that's what accounts for that small discrepancy. And that's why I emphasize, right, that your electronegativity is in a bond, and it's, right, how much it's pulling with another atom, versus this, where it's a gas phase calculation of just an atom. So then you have slightly different results there. So yeah, that's really the only discrepancy that we find, that chlorine is the, again, most negative, so most favorable electron affinity. And then, like the notes were noting, so your alkaline metals and alkaline earth, right, those are pretty unfavorable. And, right, we can kind of imagine, like, why would that would be unfavorable? Like, where would those electrons go? That would be pretty unstable. All right, so that's not a favorable process there. Right, good. And then obviously, right, noble gases as well, not a favorable process. So those are all endothermic. And so Lewis theory, again, this is a good kind of basic foundation for understanding kind of what's going on, where our electrons are. And right, again, it helps us kind of predict some of these properties. So again, we're just like slowly building up our understanding of our world, why things are the way they are, why things, you know, are solids, liquid, gases. And so then, again, right, this is our ionic model is showing us kind of all these properties. And so again, right, if we disrupt our ions, obviously we have those repulsive forces. And again, our crystal can be unstable and break. Again, we're seeing why it has those properties of being brittle and shattering and shards there. And then obviously, right, there's some kind of limitations. So predicting that, right, ionic solids should not conduct electricity. And all this means is that we have to have, right, these kind of charged particles to generally conduct electricity, so being an electrolyte. And right, so ionic solids do not conduct electricity. That just means, like, if you have a pile of sodium chloride, right, it will not in itself conduct electricity. Instead, they have to have a medium to float around in. And so going back to, again, like how it dissolves in my water molecules that are floating around. So, right, we have to have this motion and these particles, right, floating around in solution to give us motion, right, to actually complete the circuit. And so, right, it predicts that both a liquid ionic compound and an ionic compound dissolved in water should conduct electricity. And again, this kind of gets into research areas of trying to, you know, develop a liquid ionic compound, because, well, most ionic compounds are solid, as we just went over, so that'd be a pretty rare material. And so again, going back to the kind of energetics, we want to be able to kind of quantify again all the parts of making our salt here. And so we have our energy here. So let's kind of look at our problem and look at it. So right, what we want to do is then look at our forces involved. And so what we find is we have extra energy, right, that comes in from the stabilized structure. So I mentioned, right, we have our crystal lattice structure, and that's obviously stabilized where every cation is surrounded by anions and vice versa. Again, going back to this picture here, right, repeating units, repeating patterns, okay. And so now our goal is to quantify this. So our crystal lattice is held together by these electrostatic attractions of our cation, right, from all these surrounding anions. And then also kind of emphasizing, right, there's no molecule. So, right, aspirin is a molecule or water is a molecule, right? They're all tied together versus, again, our crystal lattice structure where they're just repeating units. So important distinction. So again, right, we're giving the ratio of ions. So when we give a formula, right, we're giving the formula of a compound that's held together versus, right, an ionic compound. It's just our ratio. And like I said, we'll kind of revisit this thought a little later as we look into a few of the crystal structures. But basically, again, right, all we need to take away right now is that our crystal lattice maximizes our attractions between cations and anions, leading to our most stable arrangement. So again, just kind of thinking of what's thermodynamically favorable. And so let's go through, again, this process, right? So we're looking at our reaction. So sodium plus our chlorine gas gives us sodium chloride, and breaking down each step. And so, okay, we said then half of the process, right, is our ionization energy. So our sodium giving up our electron. And so again, right, we can quantify that. We can relate it back to these calculations. Okay, so this is our ionization energy, and this is given in kilojoules per mole. And we can see, right, it's endothermic, meaning that it has a positive value. So basically we put energy in. So energy needs to go into the system. And then, okay, so our electron affinity, right, looking at that calculation. So again, measuring the energetics of that. What does it take for our chloride to add an electron? And okay, let's look at where we're at. So we kind of have a small issue. So we have 496 and then plus my negative 349. And so that has a positive value, right? And so that doesn't really sound favorable. So we added those two numbers. And so this is what that statement is saying, right? So we're saying, okay, our ionization energy of our metal is larger than our electron affinity. So we would expect the formation of an ionic compound to be endothermic, just based off of these two factors, right? But then kind of what's the problem with that? And you can also kind of reason this out as well, right? But an endothermic process, well, it needs energy. So generally that's not favorable, right? We're not getting into kinetics yet, so that's second quarter. We're just talking about energy in or out. But then it also tells us that the formation of most ionic compounds is exothermic and large. So why is that, right? So right now, again, we added those two numbers up. We got a positive number, so that's telling us it's endothermic, energy in. Well, where's this missing factor, right? We're not accounting for it. Well, it's all from that crystal lattice. So that's what's kind of amazing, right? And so this extra stability that allows for the formation of the crystal is then our lattice energy. And so again, it's our energy released when our solid crystal forms from separate ions. And so it's going to be exothermic, as we might imagine. And so again, right, favorable process as these come together. And so lattice energy is measured directly, but we can kind of roughly calculate it and again get these electrostatic forces. And so it's going to depend on the size of our charges and inversely on the distance. So let's look at that. So we have our formula here. So our separation from 2 points is equal to, and of course this is just a constant, so 231 attajoules per picometer. So make sure that you're in picometers, right, for your distance here for this formula to work. And then we have Q1, Q2. So, right, this just means our charge 1, charge 2. And so let's practice this for sodium chloride, right, and see what our Coulombic energy would be roughly. And so when you go do these calculations on your own, I expect there to be like minor discrepancies, by the way, on the distance. So the two different ways to do it is like, right, you could actually go on the internet or whatever and try to actually find what the crystal structure difference is, right, the true distance between sodium and chloride. I'm not generally expecting that. What I expect is we can go back to this chart. So this is from your book, right? So your book should have a chart of all your different radii, right? So we can use these numbers for our radius. So our sodium cation radius, right, is 95. And I would just add our two radius, right, to find our distance. So 95, and then chloride over here is 181. And so that's at least good enough for the distance between them. But like I said, I totally expect there to be discrepancies because it depends where you get your data from. And so then just real quick, kind of running out of time here, but I just want to show this calculation. So then, right, obviously sodium's a 1+, chlorine's a negative charge. So we can plug this in. And we said, like I said, our distance was roughly 276 picometers. Again, your number will vary. And then we can plug it into our formula. So 231 attajoules times our picometer. And again, units. And so then we get 231 divided by 276. And so we should have negative 0.837